Exploring the Solar System Part 2, how we explore the solar system using spacecraft. I'll be talking about how we get there, how we get spacecraft to other planets. Once we've done that, what do we do when we arrive? How do we get images back from these distant places? And again, I ask the question, what next? When I put this talk together, I thought, I wonder how many spacecraft we have sent out beyond the Earth's surface that are involved in exploring some aspect of the solar system, whether it be the immediate environment of Earth, or the Moon, or the planets, or asteroids. Just how many spacecraft have there been? I started trying to add them up and realised I didn't have enough fingers on my hand. And so I resorted to looking them up and found that after 70 years, there are an awful lot. I know you can't necessarily read all the details, but that is what's been happening for quite a few decades. Ever since the very early probes, we have been sending up dozens upon dozens of spacecraft, some of which have ventured far into the solar system. One of the most recent, I haven't included the very recent lunar missions, but one of the most recent is at the bottom right there, Europa Clipper, which I'll come back to at the end of the talk. Let's just remind ourselves how we get to Mars. If we just have a very simple view of the solar system and think of the Earth going around the Sun in a circle and Mars going around the Sun in a circle, this is not to scale. If we want to go the most fuel efficient way from the Earth to Mars, we leave the Earth when it's in the position as shown here, and we arrive at Mars in the position shown at the top there, even though Mars is on the other side of the solar system. The actual trajectory taken by the spacecraft is shown by that blue ellipse. In other words, it's an ellipse where the closest point of the Sun corresponds to the Earth-Sun distance, and the greatest distance from the Sun corresponds to the Mars-Sun distance. And that can be achieved with the smallest kick from Earth, and then a kick again when you get to Mars with your rocket to put you into Mars orbit. So that is a reasonably easy way of getting to Mars, and that's one of the reasons you don't need a very large rocket, even if you're trying to send a few tons to Mars, a big rover. It doesn't need to be a large rocket, simply because you don't need a big acceleration to leave Earth orbit, and you don't need a big acceleration to go into orbit around Mars. That's what the orbit actually looks like. You might get the impression that if you go to Mars and decide not to land, then that's great because you simply come back to Earth again. Well, not quite, no, because it takes about a year and a half to cover that blue orbit. And of course, in a year and a half, the Earth has moved round the Sun once and then around the Sun with half an orbit. So the Earth won't be there anymore. If you go to Mars and then stay on the blue line, Earth isn't where you left it. That's one of the problems with going to Mars. You can't really do it quickly. A Mars mission, if it was a manned mission to Mars, you would have to bank on going to Mars, staying there for a little while, waiting until Mars and Earth are in the right position, and then coming home again. So the mission would be something like 2 years. Going to the Moon and back, 2 weeks. Going to Mars and back, 2 years. A much bigger undertaking, which is why we haven't done it yet. But in terms of getting to other planets in the solar system, well, in the 1960s, it was realised you could use a gravity assist. The purple shows us going past Jupiter and getting a kick as we go past Jupiter, accelerating us to a much higher speed and then sending us on towards Saturn. This happened in the Pioneer spacecrafts and here shown for the Voyager 1 spacecraft. Realizing that the planets were lined up such that as you go past Jupiter, you can get a gravity assist, or a slingshot as it's sometimes called, means that not only can you go faster, which means that you can get to your final destination more quickly, it also means you don't have to fire rockets as often, so you have less fuel to carry. If you have less fuel, that means you can have a bigger payload and hence more scientific equipment or more cameras. So it's a win-win scenario to use the gravity of some planets to get you there faster. And in the case of Voyager 2, that was the grand tour in which it left Earth orbit, got a gravity assist from Jupiter, which sent it on even faster to Saturn. When it flew past Saturn, it got another gravity assist and threw it on even faster to Uranus, and then again another gravity assist to send it on to the planet Neptune. So of course they had to get the timing right to make sure they arrived at the right time when the planets were in position, but it meant that Voyager 2 could explore most of the outer solar system with barely any rocket fuel at all, as long as you can get these gravity assists. Great idea. So let's have a think about what you do when you get there. You want to send images back. I'm not sure if anybody knows what image this is. If I tell you which spacecraft took it, you will immediately know what the image is. This was taken by Luna 3, and it is the far side of the moon, taken in 1959. Not the familiar near side, because the moon is tidally locked. This can only be imaged by spacecraft never seen from Earth. We can tidy it up a little bit, do a little bit of noise reduction, and you can see the resolution is fairly poor. We can see a few dark areas and see a few light areas, but we can't see much else. But bear in mind the technology that allowed us to get this picture in the first place. This is before we had digital cameras. So that image was obtained by having film emulsion, which was exposed, and then the film was developed inside the spacecraft, and then it was fixed and dried. Then the film was scanned with a cathode ray tube, a flying dot, a flying spot if you like, projected through the film onto a photomultiplier which picked up the brightness of the light, and that signal was then transmitted back to Earth, and the image reconstructed, much like in a fax machine. So it was an extremely laborious process to be able to expose film, develop it, scan it, and send the information back. If we compare with a much more recent image taken with digital technology some 50 years later, notice that, well, the original pretty much got it right. The dark areas, the light areas were all imaged correctly. It didn't have the same resolution that we currently have, but it did tell us that the far side of the moon does not look the same as the familiar near side of the moon. It took until the 1960s before we had digital technology, and Mariner 4 and Mariner 5 were the first spacecraft to have digital cameras. In fact, these were the first digital cameras. They were developed for spacecraft. The fact that you have a digital camera in your phone is a result of spacecraft needing digital technology, and over the years that has spun off to the digital imaging technology that you probably currently have in your pocket. So these digital cameras took images of Mars as they flew by. Those images were stored on a tape loop, and it was hoped that the loop would stop once the spacecraft had passed the planet. Otherwise, it would simply keep recording what the cameras were seeing, which would be nothing, 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 nothing. Luckily, everything did work correctly, and then the tapes were read back and the images transmitted back to Earth. The first images of Mars in the middle of the 1960s. Again, we can tidy that up a little bit with noise reduction, and we can see obvious features, light and dark, and we can see various craters on the surface. But this was a much better way of taking images. Rather than developing film and scanning it, we could now take relatively large amounts of data. We still have to record it and then transmit it, because the transmission speeds were relatively slow and it took a long time to transmit an image back to Earth. So it might pass the planet very quickly in an hour or two, but it could take days or weeks or months to transmit the data back to Earth. We've effectively explored all of the planets, some of the smaller dwarf planets, some of the asteroids, a lot of the moons, etc. of the solar system. We've effectively visited all of the major bodies in the solar system. Let's just have a very quick look at a couple of those missions. Cassini, launched in 2004 and eventually crashed into Saturn in 2017. It was crashed into Saturn to make sure it didn't crash into any of the moons, because the moons are thought to be the possible sites where life might exist, whereas it's thought unlikely that Saturn itself has any life, and therefore it's far safer to crash the spacecraft into Saturn to avoid contaminating any of the moons. So I'm not going to talk through all the numbers, but clearly there's some incredible numbers there in terms of the number of images taken in the bottom right there, something like 500,000. We know that it's travelled billions of miles over the years, and the data it's collected has resulted in thousands of scientific publications. In the bottom right, you can get an idea of the size. These spacecraft are by no means small. You can see they're many, many meters high compared to the size of a standard human there. If we compare a picture from Hubble, an image from Hubble of Saturn, we can see some nice detail. But if we think about the detail we can see in the rings, once Cassini got close, we realized that it was able to resolve much, much more detail than we can possibly see from Earth. The closer we got, the more the ring system looked like a long playing record. Very flat. The ring system might be 250,000 kilometers in diameter, but in places it's only a thickness of a few meters or perhaps tens of meters, despite the diameter being 250,000 kilometers. When the sun is in the plane of the ring system, we find that it actually casts shadows. So although most of the ring system is flat, some of it appears to be bumpy. And when the sunlight is almost in the ring plane, we can see these bumps actually cast shadows onto the rest of the ring system. The bumps themselves might be a few kilometers or so in height, compared to the smoothness of the rings, which might be measured in meters. And so by looking at the ring system and these bumps, we can get an idea of the dynamics of how these various particles, remember there are some trillions of particles of ice that make up the ring system. None of the ring system is solid in that sense. Lots of independently orbiting ice particles, and the dynamics of how they move and how they gravitationally interact with each other tells us about the ring system. One thing you can't get from Earth is this view where Cassini flew into Saturn's shadow. We can only see Saturn sunlit, as it were, from our side because we are fairly close to the sun. But here Cassini has flown into Saturn's shadow, and we're seeing the ring system lit from behind, from our perspective. And because the sun is shining through the ring system, that allows us to get information about how sunlight is scattered, and that tells us about the sizes of the particles. The different brightnesses we see here are telling us about the different sizes of particles in the ring system. So again, a very important part of the jigsaw to give us an idea of the dynamics of how the ring system came to exist and what its future might be. Sitting on the side of Cassini is a little interloper there, a Huygens probe. It was thought that as well as exploring Saturn, why don't we send a little probe which we can drop into the atmosphere of Titan? Titan has a very dense atmosphere which we really can't see through, and therefore we couldn't really tell what the surface of Titan looks like. It's a very big moon, and it was thought worth exploring. So Huygens was bolted onto the side of Cassini and then released in 2005 to land on Titan. And as it came in on a parachute, a video looked down to see what the world of Titan actually looks like. And as Titan plunged through the atmosphere, it found that Titan is a world with mountains and lakes and rivers and clouds and rain, much like Manchester basically. But it's a world in its own right. It might only be a moon, but it's a relatively large moon, and it is absolutely an interesting world in its own right. And that's why there are plans for instance, the Dragonfly helicopter to go back to Titan and explore more of this rather wonderful world. Let's have a very quick look at Juno, a relatively recent spacecraft, 2016. It arrived at Jupiter after a 5-year journey, and again, I won't talk through all the numbers, but it's travelled billions of miles. It's had huge numbers of instructions: point at this moon, point at Jupiter, explore this, explore that. Changes to its orbit, as well as telling the cameras what images they want to get next. Terabytes of data collected over the years it's been exploring Jupiter. If we think of a simple image of Jupiter and unwrap it so that we can see all of the bands, it's clear that there are lots of bands. These are winds effectively travelling in different directions, and the great red spot there is a storm system that's been raging for hundreds of years. We'd really like to understand why storms on the Earth dissipate relatively quickly, but it looks like some storms on Jupiter can last for hundreds of years. Why the difference between these two weather systems? The different colours that we see in visible light here, the oranges and the salmon colours, we think that's the result of different compounds absorbing visible light. So there's probably sulfur and phosphorus in there, and perhaps we're looking at different levels in the atmosphere, as well as different wind speeds travelling in different directions. As Juno swooped towards the planet, we get a really detailed view of the cloud tops. Those little flashes of white that you sometimes see, that's lightning in the storm systems of Jupiter. And we can see incredible detail because it's swooping only tens of thousands of miles above the surface. As it comes in, we see a huge amount of detail, and then Juno moves in a very eccentric orbit much further from the planet. There it's sweeping by and looking back as it moves away from the planet. Again, some very interesting looking storm systems there, those white circles. The equator tends to be a orangey colour, the poles look a little bluer. If I just have a still from that, we can get even more detail. So again, trying to understand these storm systems by having a close look every once in a while and then pulling back with a highly elliptical orbit. Juno can spend a lot of its time away from Jupiter and then sweep in for a close look every few months or so as it goes around Jupiter and continually takes a swoop over the equator and over the poles. Trying to understand exactly what these storm systems are and why we get the winds working the way they do will help us understand the weather systems on Jupiter, and maybe it'll even help us understand a little more of the weather systems on Earth. But the solar system is not just the Sun and 8 planets. New Horizons, for instance, has explored beyond Pluto. Pluto is now a dwarf planet rather than a planet. And after Voyager has been past Jupiter, Saturn, Uranus and Neptune, it was decided that we really want to explore Pluto and beyond. And so the New Horizons spacecraft was flown past Jupiter. Of course, it takes years to get there, but now it's on its way beyond Pluto into the Kuiper belt, and it's trying to take a peek at some of the objects that are out there. The Kuiper belt being a large belt of icy bodies a long way out beyond the orbits of Neptune and Pluto. But in addition to the planets and dwarf planets, there are also over 300 moons to explore. Here's a very small selection of them. They're not to scale. Some of the larger ones tend to look close to spherical. There's the rather hazy Titan, where we can't really see the surface, but there's clearly a very thick atmosphere there. Some of the smaller objects tend to be more potato-shaped. There's one that looks like a pizza. That's the moon of Jupiter, Io. Some of them look really weird, like a walnut. Some of them look more like the Death Star from Star Wars than they do spherical moons. If we show some of the larger moons to scale this time, again, there's Titan in the middle, showing a rather hazy atmosphere and no surface. And our moon is there on the right-hand side for scale. But a lot of interest recently has been focusing on the moons of Jupiter. On the left, the top there is Io, the thing that looks a little like a pizza, a very volcanic moon because of its distance from the surface of Jupiter. But a lot of interest recently in the ice moons. So you might say, well, that's a little boring if all they are just lumps of ice. But it looks like they have ice on the surface, but they have water oceans underneath the ice. There might be more water in these moons than there is over the entire surface of the Earth. In other words, if you took all of the Pacific and the Atlantic and the Indian and the Antarctic Ocean, you would have more water on Europa, Ganymede and Callisto than you would anywhere on Earth. So if Earth has produced life as a function of giving liquid water time to develop life as well as an energy source, well, if there's liquid water on these worlds underneath the ice, then there's an energy source keeping these things liquid, and perhaps life exists in the oceans underneath the ices of Europa, Ganymede and Callisto. And that is precisely why there's interest in sending probes to specifically look not necessarily at Jupiter, but at Jupiter's icy moons. So ESA have sent the mission JUICE, Jupiter's icy moons, and NASA have sent the mission Europa Clipper. So these have been launched in the last couple of years. They'll take a little while to get there, but they are specifically trying to find more information about the subsurface oceans on these worlds. I was talking about how you get the information back, sending images back on radio waves. That's how it's been done for the last half century or so. But there are other ideas. One option is, you just keep using radio. You have a large dish on the spacecraft and you send the radio signals and pick them up on an even larger dish on Earth. That's tried and trusted technology. We've been doing it for decades and it works. But the question is, could we do it better? Is there a way of getting a much higher data rate? Now that we're taking high resolution images, and lots of them, remember we're taking terabytes of data when we take high resolution images of planets and moons, and we're now taking videos as well as images, is there a better way of getting those data of those images and those videos back to Earth? One alternative to radio is to use lasers instead. Lasers work at a different frequency, they have a much higher transmission rate, and they need less power. And instead of a large radio dish on Earth, you would just need an optical telescope. And as a test, the 5-meter telescope shown in the bottom right there, the Hale telescope, the 200-inch or 5-meter mirror telescope on Palomar Mountain in California, that was used to pick up a test of a laser sent from a probe sent into the asteroid belt. What image are you going to send as a test? A simple image is not really a test because you want to send a huge amount of data. So they decided to send a high definition video. What video do you send on a laser beam? Well, they thought with a little bit of humor, why not send a video of a cat chasing a laser? So that's the video they sent. And even though the spacecraft was at a distance of 50 million kilometers, they still achieved a data rate of 260 megabits per second, which is faster than some people can get on their broadband from a server that's 10 miles down the road. Even when the spacecraft was in the asteroid belt at a distance of some 400 million kilometers, they could still achieve a data rate of 8 megabits per second, much faster than can be achieved by sending the equivalent data on a radio beam. So although this is not standard yet, this test has shown that this is definitely viable. You can get, with less power, you can get a higher data rate on a laser than you can on a radio beam. And therefore in the future it might well be that although radio is going to be with us for a little while, it might be that more and more spacecraft, especially those sent out to study the solar system, those spacecraft will be sending back their data with lasers. So again, if I pique your interest, you can find out more. There's a mission on its way to Mercury, Bepi Colombo. That's been using gravity assists to slow down in order to get to Mercury. Cassini is no more. It's been crashed into Saturn. On the left-hand side, New Horizons is continuing to fly out of the solar system. I've said that Juno arrived in 2016. It's coming to the end of its life now. And right at the bottom there, these are the relatively recent launches of the JUICE, the ESA JUICE and the NASA Europa Clipper missions, which are being sent to find out more information about Jupiter's icy moons. So there are web pages there. I'll give you a handout. I'll make a handout available, so don't worry about making a note of any of these web pages. If you're interested, you can find out more about the history and the future of these missions by going to these various websites. Thank you very much.